Hi, I am Rishabh Patra. I am an undergrad at BITS and I'll be presenting this paper titled Calibrating Deep Neural Networks Using Explicit Regularization and Dynamic Data Pruning. So to motivate this problem, I'd like you to imagine a COVID-19 ward where we use a deep neural network to decide whether a patient goes to the COVID ward or a regular ward, just based on an X-ray. If the model decides with high confidence, that is greater than 95% that the patient is COVID negative, they are sent to the regular ward, else they are sent to a COVID ward where doctors perform more conclusive tests. Here, calibrated and confident models are very crucial. The problem here is model calibration. So this is a reliability diagram which is used to measure the trustworthiness of a model. This is trained on this is a ResNet 50 trained on CIFAR 10. The y equal to x line denotes perfect calibration where confidence matches the accuracy, where the confidence is plotted on the x-axis and the accuracy is plotted on the y-axis. Here, most of the bars lie below the y equal to x line, which means that the confidence is greater than the corresponding accuracy, hence overconfidence. It is a well-known fact that overparameterized models are often very overconfident and hence miscalibrated, which makes them unreliable and not trustworthy in safety-critical applications. So this begs the question, when can I trust my model's predictions? An ideal model would look something like this, that it's confident and calibrated, and the highly confident predictions are high in number. For example, think back to the COVID-19 scenario when 95% was the criteria to send someone to the regular ward. So our contributions in this matter are as follows. 1, we propose an auxiliary calibration loss, which is inspired by Huber loss and focal loss. And 2, we propose a dynamic train time data pruning strategy, which is inspired from calibration under data diet. And how do these look like? So equation 1 is the focal loss, which is a well-studied calibration loss. Equation 2 is our Huber loss, which penalizes the deviation of confidence from the accuracy over a mini batch. The total loss is focal loss with a regularized Huber loss. And the result is that we achieve lower calibration errors and can be seen from the reliability diagrams plotted below. Ours achieves near perfect calibration as opposed to the other contemporary calibration losses. The dynamic train time data pruning strategy works as follows. We track confidences of instances over training epochs, and we make the hypothesis that the model stays relatively underconfident over certain instances, and these instances are undesirable as they hamper the learning ability of the model. And so we prune them out at checkpoints. And how does this work out? We get an increased proportion of highly confident test samples. So you'll see FLSD versus ours. FLSD is the sample dependent focal loss. We plot the histogram of confidences, and there's a huge bump in the last bar which indicates the highly confident samples. A caveat of this dynamic train time data pruning is that we achieve reduced training times. Across CIFAR 10, CIFAR 100 and Tiny ImageNet, we achieve a reduction of around 20 to 40% using our train time pruning strategy. So all in all, our method gets the following. First, we obtain SOTA on calibration metrics across datasets. 2, our method obtains a higher number of highly confident samples compared to other calibration losses. And 3, we have a reduction in training time, which directly translates to a reduction in carbon footprint. So that is all. Thank you.